Okay, so the first speaker is going to be Richmond Sarpong. He's been a member of the center now for an extended period of time, since the inception of the phase 2, and really has been a thought leader in terms of thinking strategically and in terms of how to use CH functionalization. So Richmond, we're very much looking forward to your talk.
Okay, thank you very much, Hugh. It's a real pleasure to be part of this 14th edition of the CCHF Virtual Symposia. It's really my pleasure to present on behalf of my coworkers here at Berkeley. And today I thought I would tell you one story, but this story will be placed in the context of our involvement in the center. And so I think all of us can agree that organic synthesis, at least as we think about it, probably began in 1828 with Friedrich Wöhler's urea synthesis. And it's almost been 200 years since that time. And I think as we advance to 2028, a lot of us can agree on some of the directions that the field is going in, but perhaps there are new directions that would emerge as well. But certainly, I think all of us adhere to the fact that this inception of synthetic organic chemistry really began with the CN bond formation in the synthesis of urea by Wöhler. However, in the ensuing 190 years or so, the field has really been driven by carbon-carbon bond formation. And of course, this is primarily due to the fact that a lot of the targets that one looks to address with organic synthesis are really based on a carbon framework. And so carbon-carbon bond formation has really formed the basis for advancing the field. And here are some examples of the types of target molecules that one can address using carbon-carbon bond formation primarily. But of course, carbon-carbon bond cleavage is also an important aspect of synthetic organic chemistry. And so here I show a few examples of the types of carbon-carbon bond break-in reactions that have been part and parcel of synthetic organic chemistry. And most of these are attended by a bond-forming process as well. And by far, the most sort of historically relevant carbon-carbon bond cleavage reactions in organic chemistry have to do with cases where you have either a functional group that's proximal to the bond that's being cleaved or a latent functional group, for example, a double bond being proximal to the bond that is being cleaved. And so we asked the question whether there's any value in cleaving carbon-carbon bonds in a general way, even in cases that might be devoid of the sort of traditional functional groups that we think about. And of course, a lot of this is inspired and driven by lessons from sort of the state of the art when it came to thinking about carbon-hydrogen bond cleavage and functionalization. And so in a classic example, one can think perhaps of the deprotonation of a carbonyl compound at the alpha position as an example of a CH cleavage in the traditional sense. And of course, this then is followed by a bond-forming process where an electrophile is introduced. But the field of CH functionalization is, of course, advanced tremendously. And here are a few examples of the types of CH cleavage reactions that are then followed by bond-forming processes that now can be effected even in the absence of a traditional functional group being proximal to the CH bond that is cleaved. And of course, is the work of Hugh Davies, and this has been one of the fulcrums of the Center for CH Functionalization. Now, my group has been involved in the center, as Hugh mentioned, for some time, and our charge as part of the center was to really think about ways in which we could apply CH functionalization methods to address the synthesis of complex molecules. And so on this slide, I show some examples of the types of bond-forming processes, which are highlighted in red, which were really inspired by thinking about CH functionalization. And in general, these bond-forming processes or CH cleavage processes that are then followed by bond-forming were really driven by thinking about CH functionalization in two ways. And so for the two examples that I show here, I would say that our idea was that we could affect perhaps a peripheral functionalization of a molecule, such as the left-hand portion of this compound, complandin A, at the periphery of the molecule, which then would enable us to effect a CC bond forming reaction to bring the two halves of this molecule together. Alternatively, for this molecule, my branchiamide C, we thought about a peripheral functionalization site selectively at the C6 position of the indole. That would then set the stage for us to install the chromine that is found in a molecule like YKLoid and go on to build molecules of that type. So this is a type of CH functionalization that I refer to as a peripheral functionalization, where we're thinking about functionalizing the molecule on the periphery. The other type of CH functionalization that we thought really benefited complex molecule synthesis was one that I would term core functionalizations, where we would forge a CH bond, we'll cleave a CH bond to forge a new bond that would form part of the core framework of the molecule. And so, for example, here the idea was to effect ultimately a CN bond formation by cleaving a CH bond that resided at this position. And the same was also true here in the context of this molecule, where a CH bond would be cleaved to ultimately forge a carbon-nitrogen bond. And as we thought more about these ideas of cleaving CH bonds to forge other bonds, and especially in thinking about this in the context of late-stage functionalization, we wanted to think about ways in which one could achieve maximal diversification of molecules at a late stage. And of course, peripheral functionalizations have been utilized extensively for this purpose, but we also wanted to think about ways in which one could do this at the core of organic molecules, and that would necessarily mean thinking about ways in which one could break carbon-carbon bonds to forge new bonds. And so the idea that we had was really what we call tongue-in-cheek, our break it to make it moment, which is this idea that perhaps just as we've been thinking about CH bonds as functional groups, could we now start to think about carbon-carbon bonds in the same vein? And so I thought I would begin by illustrating this in the context of one total synthesis that we've undertaken in my group, which is a total synthesis of a molecule called Phomactin A. And this is a molecule that is a member of a larger family of diterpenoids, which were isolated initially from the backs of a snow crab found off the coast of Okinawa in Japan. So the fungus that produces these secondary metabolites resides in a symbiotic way on the backs of these snow crabs. And these molecules are interesting from a structural standpoint, as depicted here by Phomactin A, but there's some emergent interest in these molecules in terms of their function as platelet activating factor receptor antagonists. And that, of course, has a lot of implications in terms of thinking about diseases that have to do with inflammation, such as cardiovascular disease, cancer, and so forth. And so we were interested in the synthesis of these molecules, first, obviously, to address the challenge of their complexity and how one can address that with a chemical synthesis, but ultimately with an eye toward also bringing perhaps some insight into the function of these molecules. And so as we consider the family as a whole of the phomactins, what we came to appreciate is that all the congeners in the family actually have the same carbon skeleton, which is depicted here in this blue rectangle. And one thing that seemed to be the case is that if one thought about biosynthetically how these molecules arise, it may be the case that a late stage P450 sort of tailoring mechanism would account for how oxygenation is achieved in all of these molecules. And so we worked with an isolation chemist actually, because we thought that there must be opportunities for other types of oxygenations. And so working with Professor Roberto Berlink from Brazil, we were able to isolate additional members of this family, which indeed also had the same carbon skeleton, but differed in terms of the oxygenation. And so we were confident that if we could identify a common carbon framework, we could then perhaps achieve diversifying oxygenation at a late stage to build these molecules. And so that led us to identifying this particular compound in the bottom right as a common synthetic intermediate that we could apply to address the syntheses of all the phomactins. So I'll fast forward and just sort of give you a bit of an overview of the existing syntheses at the time that we began our work. Several groups have indeed achieved syntheses of individual members of the phomactin family. I note some of these contributions here, and these are nicely summarized in a review by Alison Frontier's laboratory. And the gist, at least in terms of the syntheses that produce material in an enantiomer-enriched form, is that there was a lot of steps that were invested in building what I would call the cyclohexene portion of these molecules, which is a 6-membered ring which resides here in the framework of Phomactin A. And so we thought if we were going to make any contributions in an impactful way to the synthesis of these molecules, we had to find a way to achieve the synthesis of this portion of these molecules in a shorter step count. And so our idea was that our common synthetic intermediate that we had identified could be brought back to these 2 fragments. The vinyl iodide had been utilized by Yamada in his group synthesis of the Phomactins, and so that we would borrow in terms of how to prepare that, and really the contribution that we're going to make really rested on our ability to prepare a cyclohexene fragment of the type shown here. And that we thought we could bring back to a precursor such as this compound here, carbone, which is readily available. Either an enantiomer can be obtained in metric ton scale. And so we thought that would be a great starting point to address the cyclohexene fragment. And so the key question then became how we advance carbone to this particular fragment. And so in that regard, we thought that if we start from carbone and we're able to build a bond between this blue dot and this blue dot, that would enable us to forge the CC bond that I showed here. And so that would then lead to a tetrahedral intermediate. And our idea then was to cleave this carbon-carbon bond in that tetrahedral intermediate. And of course, because carbanions are bad leaving groups and not great leaving groups, we thought we would do this with the sort of assistance of transition metal catalysis. And so I wouldn't go through this in detail here, only to say that, of course, pi bond activation, one can readily achieve. CH bond activation is much more challenging because of the orientation of the CH bond sort of orthogonal to the d orbital system of the metals. But of course, due to the s orbital of the hydrogen, one can now arrive at an agostic interaction that ultimately leads to activation of the CH bond. A CC bond activation, on the other hand, becomes even more challenging because the d orbitals have to become proximal to the sigma bond for the CC bond. And of course, each of these carbons bear substituents that makes it difficult to achieve that level of proximity. Now, our field has contributed tremendously to ways to think about CH bond activation. And so here I list some of the current leaders in this area. And I think a lot of the insight that's been brought to this is that if one can actually constrain a carbon-carbon bond in a small ring, you can achieve a rehybridization of that sigma bond. And so, for example, in cyclopropane, we can think about the Walsh orbitals that arise where there's more emergent p character to that carbon-carbon bond. And so kinetically, that now makes it possible to have a more pronounced interaction with the d orbitals of the transition metal. And so that's a kinetic argument. On the thermodynamic side of things, of course, carbon-carbon bonds are strong bonds, whereas in many cases, carbon-metal bonds are relatively weaker bonds. And so if you can associate the cleavage of the carbon-carbon bond with a strain release, such as that which is achieved in cleaving at cyclopropane, that can enable one to ultimately arrive at either a thermoneutral process or perhaps even an exergonic process. And so that was our idea then, was to adopt this plan to introduce strain into the carbon-carbon bond that we're seeking to cleave. And so we could take carbone, epoxidize this isopropanol group, effect a reductive CC bond formation with opening of that epoxide, which proceeds through transition states that are sort of depicted here in cartoon form, ultimately leading to these 2 bridged diols. And so these look somewhat esoteric, but in fact, these are simply hydroxylated versions of pinene. And so if one were able to site selectively hydroxylate pinene, you would arrive at these compounds. But of course, pinene hydroxylates at the allylic positions, which are much more activated to give verbinol and mertenol. And so this is sort of a roundabout way to get to these particular hydroxylated pinenes. And so with those compounds in hand, which are now, of course, bear the inherent strain of the bicycle and also the cyclobutanol, we could affect cross-coupling reactions that now involve cleaving the carbon-carbon bond. And so, for example, in this particular instance, we could start with an oxidative addition into this carbon-halogen bond that then is followed by a ligand exchange onto the tertiary hydroxy group, and then a beta carbon elimination proceeding through the sort of four-center transition state, ultimately terminating with a reductive elimination would lead to this particular compound. On the other hand, if one uses a rhodium complex, one can terminate with a protonation event to arrive at this particular compound shown here. And so in that way, we can now achieve sort of a rearrangement of that particular skeleton where we subsume this isopropenyl group into the ring and release this methylene as a methyl group through 4 steps to now arrive at this compound that I show here on the right, via the intermediacy, of course, of the cyclobutanol through the process that I just showed on the previous slide. And so following a sequence of steps, which described here, I won't go through this in detail, we could prepare our common synthetic intermediate in a total of 16 steps. And with that common synthetic intermediate in hand, we could now drive a series of oxygenations using the secondary hydroxy group to direct those oxygenation events. And so, for example, directed now vanadium mediated epoxidation at low temperature affords this particular epoxide, and then oxidation of the secondary hydroxy group affords Phomactin R. One could then effect an epoxidation of this more distal double bond to afford Phomactin P, and an alytic oxygenation then affords Phomactin K. If one carries out that epoxidation at a slightly warmer temperature of 0 degrees Celsius, one can effect a double epoxidation, and this then enables us to get to all the other Phomactin family members that represents the structures of the Phomactins in 20 steps or less for the whole family. And so we've now taken this idea of CC bond cleavage by intermediacy of the strained rings and applied it to the syntheses of other molecules. And so, for example, one can begin with carbone, take that on to the cyclobutanol shown here, and utilize this now to drive a palladium-2 mediated CC bond cleavage, CC bond formation cascade, ultimately leading to this bridged tricycle, which then has been taken on to a synthesis of this molecule, isocyano ubiquinone, in our laboratory, and work led by Melissa Hardy and group. Alternatively, one can advance carbone to this bridged bicycle, again, bearing a cyclobutanol, and effect a cascade process where we cleave the CC bond to forge now a new CC bond, and ultimately take that on to molecules in the Jijicorin family of molecules. And in one emergent example from our group that we're very excited about, in work led by Brian Wong in the laboratory, we can take carbone and advance it to these 2 fragments, and then bring them back together again through a CC bond cleaving, CC bond forming reaction, and then finish up with an aldol reaction to prepare the core structure of the taxoid molecules in a total of 15 steps, longest linear sequence to get here. And we're now at the stage where we're completing the sort of site-selective oxygenations to finish this off. We've been able to achieve each of these oxygenations individually, and we're now sequencing them to finish off molecules such as taxajophene. And so the question is often asked how we can perhaps take some of these ideas and move them on to apply to what many would term pharmaceutically more relevant systems. And so to me, this is a bit of a question that I really never really understood, and so decided to delve a little bit deeper into understanding what a pharmaceutically relevant system would be. And of course, if one takes a look at sort of the existing table of the most prevalent heterocycles in pharmaceuticals, the piperidine emerges, and again, this is borrowed from a table from Jon Hjartarson's laboratory. And this is for good reason, because if one looks at a number of the pharmaceutically relevant molecules out in the market, you quickly come to appreciate that the ability to have a piperidine ring, which is then substituted with various substituents can now lead to a range of activity. And so in general, there's been a lot of interest in being able to program the site-selective functionalization of piperidines in a controlled way. Now, of course, this is not a new idea, and this is an idea that many have thought about before. Our laboratory has become interested in this, and if one looks historically about at how this has been done, one only needs to look at the work of, for example, Peter Beek or Gideon Frankel and others that have contributed to this area, Bob Gawley and so forth, to appreciate that in the past, really a big push in being able to functionalize piperidines was to utilize, for example, a Bach carbamate to direct a lithiation event. And then at that stage, one can envision a transmetallation, for example, to a Negishi precursor nucleophile. And then you can carry out the Negishi type cross couplings to your heart's content. Okay, and more recently, contributors to this area include Ian Coldham, Paul Nochel, and Olivier Badouin. Of course, in this center, there have been a lot of contributions given the fact that these types of lithiation events are strongly basic and there's less of a functional group tolerance. There's been a real interest in being able to do this under functional group tolerant conditions and also to essentially couple the steps of activating the position alpha to the nitrogen and also affecting the cross coupling. And so this can now be achieved with a range of different metal complexes in the CH functionalization process. This is a very powerful way to now functionalize molecules. Of course, Jin Kwon Yu within the CCHF has been a major player in this area. And there have been, in fact, many other players, such as those that I list here. Now, we became interested in being able to essentially benefit from these existing precedent to think about ways in which perhaps we could also start to achieve these types of CH functionalization cross-coupling processes. Now, we were especially drawn to this type of lithiation event because one of the things that I came to appreciate in a lot of conversations with folks from industry is that they kind of liked the idea of forming, for example, the initial organozinc because a lot of the cross-coupling reactions that were then carried out subsequently utilize the same set of conditions. And so by dissociating the initial nucleophile formation from the cross-coupling, one could arrive at a common intermediate that you can use to diversify in terms of the cross-coupling with not only aryl halides, but perhaps even alkynyl or alkenyl halides. And so sort of taking a bit of a lesson from that, we really wanted to identify a way in which we could arrive, if you will, under very mild conditions at a functional equivalent to this organolithium. And so we thought that we could begin with these sort of photoreactive ketoamides, which under visible light conditions, we could affect what would be a Norrish-Yang process to arrive then at these alpha hydroxy beta lactams. And this then will serve as a functional equivalent to a species of that type. And so one could then imagine cross-coupling reactions where we would affect CC bond cleavage cross-coupling to either achieve an arylation, alkynylation, or vinylation. Now, on paper, this process looked reasonable and straightforward, but of course, these types of pursuits are marred with complications. And so we entered into a very fruitful collaboration with Merck Research Laboratories, working with Dr. Charles Young, who's a Merck Disruptive Chemistry Fellow. There's a program at Merck. Charles has really led our efforts to really utilize high throughput experimentation screens to really identify the best catalyst to achieve this particular process. And to give you a bit of insight as to why we needed to identify the best catalyst, I have to tell you a little bit about how we think about a catalytic cycle for this process. And so presumably we begin with an oxidative addition to our halide, and then a ligand exchange onto this tertiary hydroxy group. And at this state, one can envision either a beta carbon elimination to cleave this bond here, which we would term proximal to this ring, or to cleave this bond, which we will term distal to the ring. And so it turns out, depending on the choice of ligand on palladium or even the metal, one can drive this toward the proximal cleavage or the distal cleavage, and ultimately, for our purposes, we wanted the proximal cleavage. And so we've screened a number of complexes and ultimately arrived at this rufous palladium G4 as the best complex to enable us to arrive then at the cross-coupling of the alpha position. And so we've looked at the substrate scope for this extensively and identified that we can cross-couple in general the piperidine ring systems. We can also achieve the cross-couplings with morpholines as well as azopanes and azocanes. And these cross-couplings can even be conducted in the presence of acidic groups such as this NH group or the position alpha to the cyano group. We've looked at this for vinylation as well. Here I show one example. The yield is not the highest, but it really just illustrates this idea that one can effect the cross-coupling and then have that follow with a Prince type cyclization, ultimately leading to bicycles of the type shown here. And so as we moved from arylation to alkynylation, then to alkynylation, we had a little bit of a surprise, which is that starting from this beta hydroxy, this alpha hydroxy beta lactam, and looking at the alkynylations, we actually got a product which is the beta functionalized compound. And when we looked at this in the azopane series, what we saw was the double bond product shown here, this sort of ene-amide product, as well as the alpha alkynylated product. And mechanistically, when we think about this, we imagine that these products might be arising from the same type of organopalladium intermediate that I'm circling here, but instead of undergoing a reductive elimination to lead to the alpha functionalized products, perhaps what ensues here is a beta hydride elimination, and the palladium hydride will still be bound eta2 to this double bond and can reinsert as shown here, and reductive elimination at this stage will then lead to products such as this alkynylated compound shown here. And of course, the beta hydride elimination dissociation would then lead to these types of ene-amides. Now, this is not a new process. In fact, Oliver Baudouin's laboratory has recently identified a very nice ligand to enable one to do this from the organozinc intermediates. And this is work that was initially reported by Paul Noschel's laboratory. And so there are ways in which one can drive the beta functionalization with ligands, but of course, there's also an interplay between the ligands and the cross-coupling partner. And so what we found is that indeed the cross-coupling partner can overwhelm this process, but of course, ligands can also drive this process as well. And so we've been looking at ways in which we can use ligands to drive these processes, not only for the alkynylation, but also for arylation. And so in an early example, using this pyrrolzinone, we can now start to achieve both alpha and beta and start to change the ratios for these two products of arise. Now, the cross-coupling reactions we've been looking at are relatively mild. We can conduct these in the presence of diazarines, and this now becomes important as one thinks about bioconjugation strategies. One can do these for relatively complex precursor compounds such as steroids. And in one complex example, we can utilize these sort of stoichiometrically generated organopalladium intermediates reported by the Merck laboratories and Steve Buchwald's laboratory to now effect these types of cross-couplings as well. And then finally, we've also shown that one can carry these out in a stereospecific way. These reactions proceed with a stereoretentive cross-coupling to arrive at for example, this arylated product. And so just to recap where we are, we're very much interested in this idea of a programmed way to functionalize piperidines and other saturated aza heterocycles. And thus far, we've been very interested in the idea of alpha functionalization. We envision that perhaps we can now sequence these types of functionalizations to achieve a second functionalization. We can also, perhaps with ligand control, enable us to then achieve a beta functionalization as well to arrive at this group of products. And so this is work, this is very much aspirational. It's work that's ongoing. We have not so far been able to achieve functionalization at what I would term the 4 position of the piperidine. However, Hugh Davis's laboratory has a very powerful way to do this, and so we're actually in a collaboration with the Davies laboratory. Wenbin Liu and the group has been working with Justin Jurzik in our laboratory, and also with the Merck Research Laboratories to look at this in detail. And so this is very much aspirational, kind of where we're headed. But of course, why stop here? And so if you can do this, why not think about ways in which one can continue to sequence and program how we introduce different substituents on these piperidines. And so we hope that these keto amides will now serve as groups that will enable us to do this in an iterative way. And ultimately, these are groups that we can cleave under relatively straightforward conditions. All right, so that's the story I wanted to share with you today. Again, my laboratory is very much interested in complex molecule synthesis, and we think primarily about strategy and how we can employ different methods to build complex molecules. More recently, we've become very interested in this idea of merging CH functionalization with CC bond cleavage reactions, and we think these present new opportunities for not only building complex molecules, but perhaps also accessing at a late stage a diverse range of pharmaceutically relevant compounds. And so what remains for me to do is to thank the people who've done the work. I'm really indebted to my research group and also the current support that we have. The NSF Center for CH Functionalization, of course, is to be thanked, as well as Merck Research Laboratories for the work that I presented here today. And specifically with the work I presented, the people that have led the way, Jose Roque and the laboratories of graduate student, Dr. Yusuke Kuroda, Justin Jurzik, these have been the primary players on this work. Lucas Gottman, Karis Roberts was a CCHF summer student that came in and made quite an impact on the group on this work. And of course, our collaborators at Merck have also been great. Dr. Charles Young has really driven not only the HTE work that I talked about, but many of the intellectual directions that we've taken a number of the project directions in the group. And then finally, none of this would be possible without the CCHF. As Hugh mentioned, this is an incredible organization that really fosters innovative thinking, and we have a number of collaborations here. I gave one of these virtual symposia talks before, and I talked about some of our other work, and so I thought I would talk about some of the newer work today. But Professor Jamal Musayev, Professor Jin-Kwon Yu, and Professor Davis have been key collaborators, as well as Professor David Sherman from the University of Michigan. And so finally, I'll stop there and thank you for your attention, and I'll be more than happy to answer questions. Thank you very much.
Very nice, Richmond. A very elegant talk all around. We're running a little bit tight on time, so it's just one question for you at this stage. So your ring openings have been done with 4-membered rings, and obviously you've got some lovely examples of using it. So 3-membered rings would presumably do it even faster. Are there any synthetic possibilities there? And also with a 5-membered ring, even though you haven't got the ring strain advantage, is it possible to use really forcing conditions and get 5-membered rings to operate, either microwave or something like that?
Absolutely. So you raise very good points. And in fact, I'll mention that there is one example of a 5-membered ring opening with rhodium, and this is work done by Nikolai Krama's laboratory. Of course, this is in the context of sort of a Norbonane system, so there's the inherent strain that is resident in that system of about 21 kcals per mole spread across those 7 carbons. But I think these are all possibilities. Certainly the 3-membered rings, this has been looked at extensively. More recently, I can think of Art Oriana in Canada's looked at some of the work in that regard. For us, the important thing has been ways in which we can generate the strained ring system under relatively mild conditions to enable us to carry out these processes. And so we've sort of focused in on that. We've found that the 4-membered rings provide several opportunities. But of course, we are thinking about larger rings like 5-membered rings and even beyond. And so, I didn't talk about it today, but we are interested in not only sort of transition metal beta carbon elimination processes, but even thinking about, beta carbon-carbon bond cleavage events, sort of radical processes. And so we've reported a couple of examples of those in the context of using silver to drive some of these processes. We have some emergent examples with copper as well, which we hope will be in the literature soon. And so, yes, we are thinking broadly beyond just the 4-membered rings.
Okay, great. Well, once again, thank you very much, Richmond.